This is a capacitor, and we insert the electric slab with the electric permittivity epsilon inside it. This is the batteries, EMF epsilon 1, EMF epsilon 2, and while we insert the dielectric slab with the constant speed V, we have a current I0 through the battery with EMF epsilon 1. We ask to find the current through the resistor R1 and the speed of the slab, so we have current like this, I0. The length of the plates of the capacitor L, the distance between them D, the width of them A. The area of the plates is S. We know the capacitance of the capacitor without slab. We know EMF 1, we know I0, we know EMF 2, we know that the resistances of the resistors are equal to each other, and we will denote them as just R. The length, I already told you about this. And if we look here, we can notice that the potential difference is the same between these parts of the plates and these parts of the plates. So it turns out that the electric field here and here, they're the same. The electric fields are the same here. So it means we can consider this system as two capacitors that are connected in parallel to each other. One with the dielectric slab inside, another one without it. So it's just air or vacuum here, doesn't matter. This is the problem itself, and I will start solving this. If we can consider this as two capacitors in parallel, we can say that at any instance of time, the total capacitance is C1 plus C2. C1 is epsilon 0 AX over D. This is that part that the electric slab already inside. And C2, it's just epsilon 0 A L minus X. Okay, of course over D as well. Over D as well. Yeah, so let's rewrite it a little bit as epsilon 0 A over D times epsilon X plus L minus X. Or I also can rewrite it as epsilon 0 A over D times L plus X times epsilon minus 1 parenthesis. Oh, nice. This is the total capacitance at any instance of time. And I can rewrite this X as Vt, because X, this is that distance that the slab has already covered, and it's inside the capacitor. So I can say that the capacitance as a function of time equals epsilon 0 A over D times L plus Vt times epsilon minus 1 parenthesis. Okay, so this is the equation for capacitance. We will use it later. Now let's analyze the circuit. First, you can think about Kirchhoff's law, or just about law of conservation of charge. I0 equals I1 plus I2, of course. I0 equals I1 plus I2. Okay, let's analyze the loop, this loop. And let's analyze this loop. You can think about it as of second Kirchhoff's law, as of conservation of energy law, or you can think about it in terms of potential. Anyway, you will get the equation like this. I1 equals EMF 1 minus the voltage drop on the capacitor divided by R1. And you will get the equation for I2. It's EMF 1 plus EMF 2 minus the capacitor's voltage divided by R2. Okay. So the total current I0 equals the sum of them, right? So we will get 2 EMF 1 plus EMF 2 over R minus double capacitor's voltage over R as well. And then we can say that the voltage drop on the capacitor over R equals 1/2 to EMF 1 plus EMF 2 over R minus I0 parenthesis. And we can see from this equation that the voltage on the capacitor is constant for sure. Of course it's constant because it's always connected to the constant potential difference. So the voltage drop is constant. We also can see it from this equation. Everything is constant here in this equation. It means VC is constant as well. So let's say VC equals constant. EMF 1 over R1 minus VC over R1, or just R. We can denote them as just R. And let's rewrite this as EMF 1 over R minus, then we'll have EMF 1 over R again, then we will have minus 1/2 EMF 2 over R plus 1/2 I0. Yeah, like this. So I1 from here equals I0 R minus EMF 2 over double R. This is our current I1. This is the answer for current. Now the most interesting part of this problem, it's about the speed of this slab. The charge on the capacitor's plates QC could be derived as the capacitance of this capacitor at any instance of time times the voltage on this capacitor. And we remember that this voltage is constant. We also know that current in general is just time derivative of charge, right? It's dq over dt, and it's positive in our case, by the way. It's positive because we know that the charge is going to the capacitor because the capacitance is increasing when we do this. So the charge is going to the capacitor from the battery, right? And we can say that the current I0 is just the derivative of charge on the capacitor's plates, QC dot. Then I can say that I0 equals dCVC over dt the derivative, right? But VC is constant. So it turns out that it's VC times DC over DT. So it means it just equals VC times the derivative of the capacitance. So we need the derivative of the capacitance. But do you remember, we got the equation for the capacitance. You can see it here, the red equation. So we just need to take the derivative of this function. If we take the derivative, we will get epsilon 0 a over d, L is 0, we eliminate t, so it's v times epsilon minus 1, right? So let's rewrite it as vc times epsilon 0 a over d times v times epsilon minus 1. Is it correct? Check it. Yeah, it's correct. Okay, let's go on. So now I can say that the current I0 equals epsilon 0, and you know what I want to do? I want to say that A is S over L, because do you remember, this is the width, this is the length. So S, this is the area of the plates. If I divide the area of the plates by the length, I will get A. So I will substitute it here instead of A, and what I will get? I will get epsilon 0 S over D times V times epsilon minus 1 times VC over L, right? Over L as well. And I can see here that this is just the initial capacitance, C0, without any slab inside, right? So I can rewrite it as C0 V epsilon minus 1 over L. That's all. This is I0 current. This is I0 current, and I will derive V from here. So V equals I0 L VC over C0 times epsilon minus 1. And we just need to substitute VC, the voltage on the capacitor, that we already derived from here. We will derive it from here, we see, and substitute it here. So we will get 2I0L divided by C0 times epsilon minus 1 times double EMF 1 plus EMF 2 minus I0R. And this is the answer for the speed. So we solved the problem.